Imagine a world where gravity, the force that keeps our feet on the ground, might not need to be quantum to create mind-bending effects like entanglement, those eerie connections between objects that Einstein himself called spooky. This groundbreaking idea challenges everything we thought we knew about the boundary between classical and quantum physics. But here's where it gets controversial. What if classical gravity theories, the ones we use every day to send rockets to space, can actually generate quantum entanglement all on their own? In this article, we'll dive deep into this surprising revelation, breaking down complex concepts so even newcomers can follow along. And this is the part most people miss. Entanglement might not be the exclusive hallmark of quantum gravity after all. While other fundamental forces like electromagnetism and the strong and weak nuclear forces have been elegantly woven into quantum theory, gravity stubbornly resists full quantization. This has spurred scientists to explore alternative paths, such as string theory, loop quantum gravity, or the notion that gravity might forever remain classical, without quantum effects. For years, the lack of experimental proof has left us guessing which direction is correct. Back in 1957, at the historic Chapel Hill Conference, physicist Richard Feynman proposed a clever thought experiment that could unveil gravity's quantum side. He imagined placing a tiny object with Planck mass, about 0.02 milligrams, in a quantum superposition, where it exists in two places at once, and letting another mass gravitationally influence it. But here's the twist. Feynman's original setup for detecting quantum gravity through this isn't fully clear from the conference notes. Nowadays, we interpret this as a way to spot entanglement between the massive objects, and several theorems insist that any local classical theory of gravity couldn't possibly create such entanglement. These theorems assume classical gravity operates only through local actions and classical information exchanges, ruling out non-local action at a distance effects, which feel unphysical. After all, interactions in nature, from electromagnetism to the Standard Model to general relativity, should be local. So, it's assumed that classical gravity can't transmit quantum information, fitting neatly into a framework called local operations and classical communication, LOCC, in quantum information theory. This means entanglement just shouldn't happen under these rules. Yet, experiments to test this idea are heating up, with numerous proposals underway and initial studies in progress, all inspired by Feynman's original spark. Scholars have debated whether entanglement truly signals quantum gravity, drawing from those Chapel Hill discussions. They've questioned if classical gravity could sneak in non-local operations that bypass LOCC and generate entanglement indirectly. But this clashes with our core understanding of nature's locality, making it generally dismissed as physically implausible. Assuming LOCC holds, we are left with classical communication, CC. The idea that classical gravity involves only classical signals feels intuitive and unchallenged, until now. We've discovered that local classical gravity theories can, indeed, produce quantum communication and, thus, entanglement. The key insight? Those theorems implicitly picture matter as following standard quantum mechanics, but in reality, matter adheres to quantum field theory, QFT, the advanced framework describing fields and particles. When we incorporate this, a classical gravitational interaction naturally leads to quantum communication. Let's clarify this with a familiar example. Quantum electrodynamics, QED, our best model for how matter interacts via electricity and magnetism, treats both matter and electromagnetic fields quantum mechanically. The interaction Hamiltonian looks like this. $\white hat H \rem int caret \rem QED F equals \int \rem D caret 3 \bf x \q \white hat A \mu \bf x \white hat \overline \psi as though \bf x gamma caret \mu \white hat \psi o \bf x e where \white hat \psi o \bf x represents the quantized fermionic field for charged particles like electrons, with q as the charge, \white hat overline \psi o \bf x its Dirac adjoint, o \white hat a if underscore \mu o \bf x the quantized electromagnetic potential, and \gamma caret \mu the gamma matrices. Perturbative calculations in QED often use Feynman diagrams to visualize interactions intuitively. For instance, The top left diagram in Figure 1 shows a first-order interaction between two electrons, mediated by a virtual photon, which acts as a form of quantum communication. For visual reference, wiggly blue lines symbolize photons or gravitons, black lines depict electrons, positrons, or other matter-antimatter particles, and double lines represent virtual particles. But here's the fascinating part. QED goes beyond just virtual photons. Higher-order diagrams, like the top right one in Figure 1, include virtual electron particles alongside the photon. Even at the lowest order, some diagrams skip photons entirely, relying on virtual electron propagators. From a non-perturbative viewpoint, there's no clear separation between virtual matter and virtual photons in QED. All electromagnetic interactions blend matter and fields. To put it simply, beginners can think of this as the electromagnetic field not just carrying the interaction but doing so through a mix of particle and field exchanges that defy easy categorization. Now, enter perturbative quantum gravity, our go-to low-energy approximation for what a quantum theory of gravity might look like. It quantizes linear general relativity alongside matter fields. The metric of spacetime, g, splits into a classical background plus a small quantum perturbation h, with the gravitational field quantized. The interaction Hamiltonian becomes $$ white hat h \rm int caret \rm qg s equals \frac 1 2 int rm d caret 3 bf fx white hat h caret mu nu bf fx white hat t mu nu bf x $, where white hat t or underscore mu nu bf x is the quantized energy momentum tensor for matter. For a massive complex scalar field white hat the phi, this tensor is $, begin array L white hat with T mu nu bf x equals white hat mathcal T mu nu white hat phi a caret dagger bf x white hat phi bf x comma partial mu white hat phi a caret dagger partial nu white hat phi dash edda mu nu partial rho white hat phi a caret dagger partial caret rho white hat phi dash edda underscore mu nu frac rm caret 2 c caret with 2 h bar caret with 2 white hat phi caret dagger white hat phi end the ray $. With m the mass, c the speed of light, Planck's constant, and the symmetric derivative notation. This Hamiltonian mirrors QED's structure closely, with photons swapped for gravitons, and perturbative quantum gravity follows QED's patterns. For two matter particles interacting, the first-order diagram, Fig 1's top left, features a virtual graviton exchange. But just like in QED, we get all sorts of other diagrams with virtual matter or graviton propagators. In contrast, a purely classical gravity theory treats the gravitational field as classical, not quantized. At low energies, the interaction Hamiltonian simplifies to $, white hat h rm int caret rm cg f equals frac 1 2 int rm d caret 3 bf fx h caret mu nu x white hat with t mu nu bf fx $. This describes matter fields in curved spacetime, a local theory akin to any QFT. Feynman diagrams for this classical setup include a cross to denote classical fields or potentials, wiggly blue lines with crosses in Figure 2.